Yeah, I'm going to be talking about how to parallelize Gibbs sampling on the GPU. In particular, there's three things that I will talk about and three things that I won't talk about. I'm going to stay at a fairly high level. We're going to talk about useful abstractions for parallelizing Gibbs sampling. I will talk about the CUDA implementation and the speed-up results that we got, and some of the broader lessons learned in the process for people who are looking to programming the GPU and just generally for scientific computing community. So I won't talk in too much detail about MCMC theory. I'm not going to get into the performance optimization discussions, and I will probably talk about why we don't do any sort of detailed performance optimization. It has everything to do with the way that the models that we use, they're built. What's the process, and how are they going to be used? What's the timelines? Because it's a little different than most of the other sort of applications of GPU parallelization that you hear about. And I will hopefully be able to talk about that too. It's pretty interesting. I can almost see a sort of a dichotomy of applications of GPU programming in hard sciences like physics and engineering versus kind of applications of these methods that tend to be on the kind of a social science or soft sciences, so to speak. And there's no unequivocal endorsement of a particular hardware or software. The results that I'm reporting are sort of very practical. What we thought was the right way to do things, what results we got, and what's the recommendation for other people. So that being said, I'll tell you a little bit about what I did before I joined my current company, what's my background, what we do. Again, it helps set the context. Why do we use hierarchical Bayesian models in quantitative marketing, which is what we do at our company? Gibbs sampling, univariate slice sample are a little bit of an introduction. Then we talk about the meat of the discussion is single-chain parallelization strategies for Gibbs sampling. Off of that, we will kind of define a taxonomy for different variable blocks during Gibbs sampling. And then we go through the three types of variables, and we talk about what's the parallelization strategy on the GPU for them. Finally, we talk about the speed-up results and sort of a total cost analysis, which is not just about speed-up, but the overall cost of developing a model, which we don't hear about often enough. I think it's important to keep in mind it's not just about the speed-up, it's about the entire experience. In particular, we'll talk about a comparison between C, OpenMP, MPI, CUDA, and even Intel's vector math library. Some of these are a little anecdotal. I don't have extensive numbers that you can sort of quote me, but I can tell you sort of anecdotally what was my experience when I tried the same code on MPI or using VML and things like that. And finally, kind of broader lessons learned. So my background is in physics. I did computational neuroscience. For my entire thesis, I used MATLAB. So I had really, not only did I not have any experience using CUDA, but I actually didn't even write C code. Until a few years ago, my kind of entry point into the family of C programs was C#. Don't ask me why, but then gradually transitioned to C++ and C, and finally my first serious exposure to GPU programming was actually 2 years ago at the GTC conference, and still didn't write any code back then. Last year, about in March, I started writing CUDA code. So our company, what do? We build quantitative marketing software. Our focus is on the food service industry. Basically, anytime you have lots of products you're selling to lots of customers, and you want to figure out what's the right price to sell these products at, or you have a company that, let's say it's spending a couple billions of dollars on marketing, and you want to help them allocate their marketing spend. Those types of questions, we help our clients answer those questions. Fairly small company, total headcount about 50, 25 application developers, 3 full-time models. They're mainly mathematicians, statisticians. Scientific computing is kind of transitioning from a one-man show, which I've been doing it, to it's more of a department. So again, this is kind of sets the context for what's the environment, and we'll talk about it even more later on. Why HB models in quantitative marketing? Because Gibbs sampling is a way to estimate these HB models. So why do we need hierarchical Bayesian models? This is sort of a very, very illustrative example. Let's say you have a retailer that's like a grocery store is selling, has stores in different parts of the state of California, in different counties, Nevada, San Francisco, San Diego. And let's say that we want to build some sort of a demand model for them, economics 101, to predict demand from price. If you change the price, the demand for orange juice is going to change in the grocery store. But the thing is, everybody knows that different demographics behave differently. So if you're in a kind of a richer, let's say San Francisco, average household income is higher than Nevada. So price elasticity, which roughly reflects the sort of the slope of that relationship, could be higher or lower in different counties. So at a high level, you may have some sort of a hypothesis about what's the relationship between different variables, but the actual coefficients could be different in different subunits of your data set. So what you then have to do is you want to build, so ideally you want to say, okay, I'll just build a model for Nevada, then a model for San Francisco, another one for San Diego, and that's perfectly fine. When I do my regression or I build my classifier or whatever I'm going to do, the outcome is going to be completely independent. The problem with that is that you're going to end up with some observation units that they don't have a lot of data points. So what happens is if you want to estimate that particular submodel independently of everybody else, you don't have enough data, so your results are not reliable. So you have to, what they call pool, you have to resolve to pooling. But then the flip side of pooling, going the complete other way, I mean the flip side of treating these models completely independently is complete pooling, which is you just drop everything into a single model. The problem with that is you're ignoring differences between the behavior of different demographic areas. So the solution, at least one kind of a robust solution, is to use hierarchical Bayesian models where you set up a hierarchy. You say, okay, those alphas and betas that describe the relationship between price and demand, for example, they're themselves governed by these hyperparameters. And the hyperparameters could be things like average household income or the ethnicity or the education index of a county. So that's sort of the motivation for arriving at hierarchical Bayesian models. And the theory behind HB models is DAGs, or directed acyclic graphs, where you basically set up a causal relationship between variables, and each node reflects the conditional probability of the child node dependent on all its parent nodes. So there's a good amount of theory behind this. But what we care about for this talk is that we use HB for handling data sparseness without loss of heterogeneity. And also we can incorporate human knowledge in the form of informative priors into the model. The important thing, this is really important, domain implications that I put down here. First of all, well, obviously for estimating these class of models, we need fast sampling algorithms. So that's number one. Number two is 2 and 3 are from a sort of a context perspective, they're really important. A priori, when a modeler, like a mathematician or a company, starts to build a model to kind of quantify a problem, they don't know what model they're using yet. It's part of the prototyping step. And that's where the distinction is between this type of modeling and when you do computational fluid dynamics or finite element analysis, you're solving Maxwell's equations with boundary conditions and all of that, because in all those cases, the differential equation is given. So you can really optimize the heck out of solving that particular problem. What we have here, unfortunately or fortunately, is that arriving at the set of equations is the first step. And what we want to enable as a program, as a GPU program, what I want to enable my statistician to do is to be able to go through that process of building that model as quickly as possible, not having decided beforehand what the model is going to look like. So that puts a kind of a different set of pressure on the model building process and the GPU acceleration angle that we're going to use. Sort of a corollary of that is that if you don't have a model specification, obviously you don't even know what are your problem dimensions to begin with. That's a sort of a less of a certain, kind of a more, a different kind of uncertainty. When you don't even know what the model looks like, you also don't even know what the problem dimensions are. Actually, what happens is a lot of times you specify your model, and for different applications of that model to different parts of your data set, you end up with very different dimensions. So again, this is important. When you do video gaming or things like that, you may have the number of pixels are defined for a different target platform or whatever. So you know you're targeting 1080 by 762 or whatever that number is. Here, the problem dimensions are not known a priori. So you're thinking more in terms of like a cuBLAST library where you have to target different, you have to have optimization path for different matrix sizes. So with that context in mind, a little bit about what is Gibbs sampling. So if you have an HP model, what you end up with is a posterior, a probability of your parameters conditioned on a bunch of data, which is a product of likelihood and prior. And what you want to do is you want to ideally calculate these expectation values of some functions of theta to, for example, calculate the average of these parameters. And that's what typically is an integral over that f of theta multiplied by the posterior. Now, if you can't calculate the integral, which most of the times we can't because the integrals, they don't have any closed form solution, you replace that with drawing independent samples. You can draw a finite set of points from the posterior to approximate the moments. So then instead of calculating the integral, you evaluate the function that you're trying to integrate over and average it over the points that you've sampled. So parameter estimation in HB modeling turns into a sampling problem. So two challenges in sampling. First of all, it's very difficult to draw independent samples from complex posterior distributions, even in 1D. And then what is even more complicated is that real-world problem space is very high-dimensional. So drawing samples from high-dimensional posterior is even more challenging. Gibbs sampling, what it allows us to do is it at least turns this problem, the second problem, reduces it to the first problem. So what it takes a high-dimensional problem and turns it into a series of 1D problems. And for those who are familiar with that, you know exactly what I'm talking about. If you don't, then this is kind of a schematic of what happens. So Gibbs sampling, and mathematically speaking, a special case of Metropolis-Hastings algorithms with acceptance rates of 100%. And in particular, the proposal function in Metropolis-Hastings is replaced with the conditional posterior. So in basically Gibbs sampling, you iterate through the parameters one by one by one by one. So you cycle through them, and in each step you draw a sample from this variable conditioned on all the values of the other parameters that you have sampled from thus far. So formally speaking, you have this algorithm. The thing that's important about this and makes this non-trivial is that that's what they call it MCMC, Monte Carlo Markov Chain. The Markovian nature of this is that each sample depends on the previous step. So it's not a typical Monte Carlo where you can generate independent samples and that's embarrassingly parallelizable. Here you have a sequential process. You're basically using the previous sample to determine how to draw the next sample. So there is no trivial parallelization angle. In some cases, we can actually employ independence, and I will talk about that. But that's not a general assumption that we can make. And the funny thing is, I'm a little ambivalent about Gibbs sampling because it makes me proud as a physicist because Gibbs sampling came into statistics from physics back in the 40s and 50s. The thing that's a little embarrassing is when it first came in, they incorrectly, the people who brought it into this field, they incorrectly assumed that they can use what they called synchronous Gibbs sampling, where you could draw all these samples. You could do like a batch processing of all of these at the same time instead of drawing this one and then plugging this theta 1, tau 1 in here. And so this makes it serial. They didn't realize that at first. They thought that they could draw all of these and then go to the next iteration, draw all of them. So they could parallelize the process of drawing theta 1 through theta n. But then somebody realized that mathematically it's incorrect. You have to go sequentially unless you can prove that you don't have to do that. And we will talk about that. So the other thing is this concept can be extended to variable blocks. And I'm actually going to use this term. By that, I mean each one of these theta 1, theta 2, theta n's, instead of being scalars, they themselves could be a vector or an array. And then you can do the same thing. And then your sampling now becomes a multidimensional sampling. But sort of the structure or the architecture of the solution or the algorithm remains the same. Okay, so univariate slice sampler. This is actually, I could have just taken this slide completely out of this, and the only thing I needed to tell you was that the slice sampler is just a great sampler. And the fact that just like any other sampler, the majority of computation time during slice sampling is devoted to function evaluation. I mean, I'm sure if any of you guys have worked with sampling or with function optimization, you know that for optimizing high-dimensional functions, most of your time is spent on function evaluation, no matter what algorithm you're using. What else could we spend our time on? It could be the time is spent on generating random numbers. But when you look at actually, you profile your code, you realize that the vast majority of time, at least in the problems that we deal with, where the functions that we evaluate themselves are pretty heavy computationally because they involve sum of contributions from thousands of data points, then the dominant factor is really function evaluation. The reason we chose slice sampler is because it's a very robust, generic, and near automatic algorithm. It requires very little tuning, as opposed to like a Metropolis algorithm where you have to pick a proposal function. A slice sampler does not need any of that. You just have a couple of tuning parameters, and they themselves are very robust. You can select, almost pre-select the parameters, and in most cases, they work out well. So they're ideal for what we need to do, which is we want to just drop it in there as a black box. And when the modeler, again, back to what I said, this is all to facilitate a prototyping process. So what we want to be able to do is we want the slice sampler to take as an argument a function, and the function is not determined right now. It's at the time when the model is built, then we know what the function is, but we want to just link it to the slice sampler or point the slice sampler to that function and have it do its magic. And it can really do that. It does a pretty good job of that. By the way, for those of you who do optimization, you can think about the slice sampler, you can consider it in your own work as a stochastic optimizer. It works pretty well. It doesn't require derivatives, which is its strength, and at the same time it could be the weakness. If analytically you can calculate the derivatives of your functions, then there might be an algorithm that works even faster than the slice sampler. But this is sort of a very good starting point. If I were to build only one sampler, I would start from this. You can also use other techniques like adaptive rejection sampling. Like I said, Metropolis is still very popular, but again, you need to kind of hard code the proposal function into that. So, and big credit to Dr. Radford Neal from Toronto, who really cleaned up this algorithm back in 2003. And when I read the paper, I thought it was just a great piece of work. So, and I've personally told him that this algorithm is great. Okay, so now single chain parallelization of Gibbs sampling. And I put the single chain here because there are ways you can parallelize, and they're embarrassingly parallelizable by spawning multiple chains. You can definitely always do that. In our application, we don't see a lot of gain from that because we usually can get this one chain to work. If we get one good chain, that's good enough. Multiple chains, it's okay, but we would rather spend our parallelization resources in other ways. So that's why I'm focusing on single chain parallelization. So there's broadly, now we're getting into the meat of the parallelization discussion. There's two parallelization strategies, block level I call it, and log posterior. What is a block level parallelization? That's available when a multidimensional conditional posterior for a parameter block is separable over the individual elements. So if you take one, let's say your entire parameter space consists of a bunch of variable blocks or arrays, alpha, beta, gamma, theta, whatever. If you focus on one of those blocks, it could be, you may get lucky enough that that particular variable block is within itself is conditionally independent, or you can say the condition posterior is separable. All right, so you can write it as a product of P conditionals on the individual elements of that. So if you can do that, then obviously you can sample each one of these theta i's independently from the other ones. So that's one parallelization opportunity. This is relatively coarse, hence it is more efficient. However, in many cases, it just simply is not available because that's not in our control. It's the problem. If the problem lends itself, if mathematically you can prove this, then you can use this parallelization strategy. If you can't, then you're out of luck. And like I said, historically, Gibbs sampling was introduced with the assumption that you can always take this for granted. And then later on, we realized that it's not that simple. The second type of parallelization we can use is log posterior parallelization. Why is that available to us? Because in most statistical models, observations are IID or independently identically distributed. So the log likelihood consists of a sum of contributions from observation points. So if X is an observation vector consisting of M individual observations, usually I can write the likelihood portion of that or the log likelihood of that as a sum over contributions from each individual observation point. So that provides a second parallelization opportunity. It's relatively finer grained, so it's a little less efficient, but it tends to be a little more prevalent in statistical modeling. unless you have time series models or other types of models where the observations are conditioned on each other. There's some kind of interdependency. Okay, so now with these two sort of parallelization angles in mind, we can create a taxonomy. All permutations of these parallelizations are possible, leading to 4 types of parameter blocks. One is that in both dimensions, they're serial, no parallelization opportunity, that's the end of it. Then you can have block parallel, log posterior serial, block serial, log posterior parallel, and block parallel, log posterior parallel. These two are single-faceted parallelization opportunities. They're relatively easy to implement. This one is very easy. This one is a little bit harder. The impact, it really depends on the nature of the problem. This one, very, very high speed up. You can literally spawn thousands and thousands of threads. Implementation is simple, but if this is only 10% of your code, then the impact is limited because of that. This one, the last one, is pretty interesting from the implementation or from a coding perspective. This is the one that actually I started working on. My first problem started with this, which is not the best way to start writing CUDA code because it was really complicated, at least for me at the time. I'm sure NVIDIA engineers could probably solve it much faster than me. But anyways, the beauty of this, using GPU, which I realized even with my very limited knowledge at the time, all I knew about GPU was that it has blocks and threads, and blocks have to be independent, threads can cooperate. And as soon as I looked at this, I'm like, great, this maps perfectly to the structure of the GPU, because you can assign each individual parameter to one block, and then you can assign different observation points to different threads. Observations need to work together because the final likelihood function is a sum over them, so you use thread synchronization for that or thread cooperation for that, but individual parameters don't need to talk to each other because they're conditionally independent, so you can put them in different blocks. There's a twist to that. That's not the most efficient way to do it, and we will talk about that. But this was very exciting. This actually, as soon as I saw this, I'm like, this is definitely GPU is going to work better than anything else because it provides me with this two-faceted parallelization opportunity that maps naturally to this. Okay, so moving on, so this is the first one where the parallelization opportunity is only at the block level. At the log posterior serial. And what we have to do is we implement the slice sampler as a device function, and then we also implement the log posteriors as device functions. And then we use this clunky way of using these function tables to pass the log posterior to the slice sampler. I have no doubt that pretty soon there would be a more elegant solution, so we can do this exactly the way we do in C, which is we can pass, it's very easy to pass function pointers around. I think on the CUDA side, at least when I was working on this, the best way to do it was to create function tables. And again, this is an example of a kind of problem that a lot of people may not have to worry about because, again, if you have a particular differential equation, you can hard code that into all your code. You don't have to abstract that out of the problem. But in our case, because we don't know what that likelihood function looks like, we have to pass a pointer to that, to the rest of the code, so that the code is flexible. But yeah, at a high level, basically each parameter gets assigned to a thread. So organizing the threads into blocks, that's kind of, from a functional perspective, is irrelevant because all threads are independent. So we can organize them in any way we want for performance objectives or whatever. One little note here is that there's something weird. I want to give some feedback to the software engineers at NVIDIA. I'm not sure if this is how it's supposed to work, but Courant library, when I try to create, actually this instead of 1 million, it's about 4 million. When I tried to create about 4 million parallel random number generators, double precision, actually it started to really act weird. The card that I was using, it was GTX 580, so it's not the greatest card for double precision, but I also didn't expect it to act like this. I expected it to be slow and everything, but it took like 30 seconds to just initialize 4 million random number generators. What I ended up having to do was I wrote my own library, and it actually worked much faster. So this is something to think about. I didn't invent any algorithm. I just used actually the numerical recipes book, and I just took that code and turned it into the GPU equivalents of that. But why is it that this was unstable, that might be a good piece of feedback for NVIDIA. Okay, so that was that, and then we can flip this around, say block stereo, lock posterior parallel. Here it's a little more interesting. Why? Because the threads have to cooperate. You assign, so you have one variable, because the thing at the block, variable block level, things are sequential, you have to go through the variables one at a time. So one variable needs to use the entire, or has the entire GPU available to it. Most of the time it's hard to saturate that, but it's better than nothing. So what you do is you just assign observations to threads. Now you can either scatter your observations across multiple variable blocks or multiple GPU blocks, and so all you can do is you can do a partial gather, and you have to do a full gather either on the host or as a separate kernel on the device, or you just shove everything onto one block, one GPU block. The price you pay is that if you have lots of observation points, that block is going to get really heavy, so that may not be the best solution. So you may end up being better off to distribute that across multiple blocks and launch a second kernel or wrap it up on the host. Now, the really interesting one is where you have both parallelization opportunities. So it gets a little more involved. I can't get into the details of the code, but at a high level, there's a couple of steps we have to take. First, we have to create a vectorized version of the slice sampler. So remember I told you the slice sampler takes a function pointer as one of its inputs. So this is the function. We typed up the function. It takes a double as its primary input, and then we kind of sweep all the other arguments for that particular function under a sort of a void pointer. That's at least one way. So the C way, not the C++ way, because in C++ you can also use functors. But I kind of actually like this. This works well. So you can kind of sweep all the arguments under this void pointer, and then you pass this function as an argument to the slice sampler. And the slice sampler takes the function as input, also takes the initial value of that parameter that you're sampling from, takes all the arguments, and then there's a bunch of slice sampler arguments that you have to pass. For example, you can create a structure and pass all of those. But when you vectorize it, you basically you are evaluating doing multiple function evaluation at the same time. You specify how many points you want to evaluate for. You pass a vector now instead of just a scalar. Your arguments are now vectors, so you pass an array of pointers. Then you also need this little thing called the select vec, a Boolean vector. I'm using a C++ syntax here. So you have this Boolean vector that tells the function evaluator, which ones to actually evaluate the function for. The reason we need this is because when you're doing slice sampling or any type of sampling, you always have an acceptance or rejection criteria. So you're going through this sort of iterative process, and at each step, some of your parameters are accepted, some of them are rejected. The ones that are accepted, you don't sample them again. You've already accepted that sample. So you need to keep track of that. And then, you're by the same token, the signature for the slice sampler also gets a little more hairy. But now, this is the first step, right? The first step is to rewrite the slice sampler, redesign the interface, and then the second step is to actually provide an implementation of that using GPU. Okay, but once you've done that, then you also write a kernel for two-level parallelization of the lock posterior evaluation for a parameter block. So essentially, you assign a particular parameter to a block, like I said, and you assign each observation point to a thread. So the summation happens within the block, so within block summation, and that's it. The blocks don't need to talk to each other. So you have this sort of nice mapping. So at a high level, it's pretty clear, right? And looks like we're on the right track. And this actually produces really good results. But the thing is, and in my initial test, I was getting great results until I actually went to more realistic implementations where the size of the groups was non-uniform. So let's talk about that. Non-uniform blocks. So in many statistical applications, conditionally independent parameter blocks, they actually correspond to non-uniform regression groups. Remember I put up that map of California and I talked about different counties, each one having its own model. Literally, each parameter here could correspond to one of those counties. Now, each store could have its own number of data points, right? Some store may have 10 times as many data points as another store. So if you have these groups that each one has a different number of observations, you end up with, at the GPU level, you end up with these blocks that their number of threads or the actual load that they have is very non-uniform. But resource allocation is always uniform, the way that we launch kernels. So what can we do? If we allocate the resources according to the largest group, then the smallest groups are wasting resources because they don't need all the threads. And vice versa, if we allocate the resources according to the smallest group, then the largest group needs to kind of serialize its kind of extra stuff that it needs to do. And the best solution, so when I looked at this, I realized this is, oh, by the way, so this non-uniformness is actually, it speaks to one of the main reasons why we use hierarchical Bayesian models. Because remember I said it's for overcoming data sparseness, meaning that some units are very small. So this was not like an artificial problem that we created to, to kind of further waste our company's resources on GPU programming. It was very much spoke to the core of why we were building this model. And also I saw the performance dropped. Because when I went from uniform groups to non-uniform groups to realistic data, I realized the gain that I was getting, if I was getting 50 times or 100 times speed up, all of a sudden it dropped to 10, 20. So I was giving up a factor of 3 or 4 or 2, and it was non-trivial. I mean, you couldn't ignore that. So we said, okay, what can we do? So you need some sort of a load balancing on the GPU, basically, which is a familiar concept when you're doing, you're using clusters. But you do the same thing within the GPU. So what we said, we need to rearrange the calculations across blocks to make them evenly distributed or as evenly distributed as possible, but at the same time avoid the need for interblock communication so as to avoid the need for multiple kernel launches. And the solution is actually best illustrated using this graph here. So let's say you have these groups and they have sort of very non-uniform distribution of observations. What we did was we basically literally wrote a very simple optimization algorithm. It's not even optimization, it's just a heuristic algorithm where we kind of plucked this group and put it at the end of the first group right here. So the 60 went over here. And then we grabbed this 89, but 89 was too, oh, I'm sorry. And the algorithm was like this. It went down the list. So if it was looking for sort of a companion for this group, for 677, to augment it, it would look at 532 and say, oh, that's too big because let's say I've selected the number of threads per block as 1,024. I can't do this one, can't do this, can't do that. It keeps going down the list until it gets to, oh, 221. That'll work because if I add it to 677, I'm still below 1,024. So by implementing that simple algorithm, we arrive at something that's a little more uniform. And the beauty of this is that each variable does not cross block boundaries. So each one is within a block. So you still have block independence, and at the same time, you have a much more uniform distribution of load across the GPU block. So when we did that, again, we almost gained back what we gave up by going from uniform to non-uniform groups. Okay, so I think, yeah, so let's look at the speed up results. And I will tell you a little bit more about what these mean. I don't want to just put up some numbers that look really amazing without explaining how they were arrived at. But I tried to be actually very fair, and I didn't have any bias. I didn't care. I just wanted to find the best solution. So block parallelization was very sort of rewarding because you literally could, so I've given the problem dimensions here. About 4 million threads were launched. Total CPU execution time was about 7 seconds. So per job, you can divide this by that and get sort of a sense of what was the duration of each job. So all of these numbers are relative to serial CPU code. We had a pretty powerful CPU. It was one of the kind of a later Intel CPUs, 3.3 gigahertz. We had a 12-core machine, but for OpenMP, we use only 8 cores. Why? Because actually the performance started to deteriorate after using about 8 cores. And I saw roughly the same behavior on a cluster because I tested the same kind of test that I did our internal server, also an external cluster. So you get good results here. For sort of log posterior parallelization, the result is not as great. Why? Because you're not saturating the GPU, and the parallelization is finer grained. But nevertheless, it's pretty decent, right? 23 times, and the OpenMP was giving us 5 times, so this was giving us an extra factor of 5 times relative to OpenMP. And when you had dual parallelization, you were getting about, again, 2 orders of magnitudes from CUDA, and OpenMP, again, was saturating at about 6 times. Again, I had made this mistake early on. I wasn't compiling. Again, it tells you how little I knew about programming when I first started this about a couple of years ago. I didn't know much about optimization flags, and so this O2, when I added it, then the comparison became more fair. Then there's a question of what kind of libraries are you using. Well, in our case, most of the time for all of these is not spent on anything that a library would help us. There was some smaller matrix multiplications, and for those, I actually, to be fair, I did not use BLAS or cuBLAS. Later on, I switched to BLAS for everything that I was doing on the host. But what I'm reporting here, I just kind of kept it as sort of a very naive implementation. They don't affect anything really, because most of the time is spent on other things, not on matrix multiplications or anything like that. Again, all the data transfers are included. I'm not reporting only the computation part, and I'm not ignoring all the CUDA mem copies. Everything is in here. So then you may ask, well, this is great, but why? Why are you getting such great results? Well, let me talk about this part. This one was pretty significant, but it's very actually logical, because when you look at the code, you realize that we are very lucky, because you break down the code, you realize 99, and these are real numbers, 99.8% of the time was spent on sampling from a particular variable block in our code that lent itself to this dual parallelization. So when you have that kind of opportunity, if you really parallelize, so this 100 times, if you actually focus on that particular variable block, this might have actually been higher. I might have put this 100 times for the entire code and not just for that particular variable block. But this is good enough, right? If we get 100 times, we're happy. If it's more than that, it's even better. So again, the conclusion from this table is that for us, it looked pretty obvious that CUDA was a good choice. OpenMP still has a great place in our sort of code development process, and I actually might have a slide about that. But so definitely, it's not knocking on OpenMP. OpenMP is, I think, anybody who does not use OpenMP as a first line of attack for parallelization, there's something wrong with that. Because why wouldn't you do that? Even the greatest CUDA libraries, they're not going to, writing them, or the best GPU programmers, they can't get you to the OpenMP version as fast as, can't you get there as fast as OpenMP gets you there? So we always do OpenMP, and then we gradually migrate our code to CUDA. That's sort of the way we think about it. Also, a mention of MPI. We tried MPI. I tried it for this one. I got about 50 to 60 times when I went to about 16 nodes, and each node had about 8 cores, so this was about 128 cores. So decent gain. The problem with MPI is that now, what's the problem that they always mention with regards to GPU programming? That it's difficult to write, it's more time-consuming, and it modifies. You have to write a lot of stuff. And why is OpenMP great? Because you just add this one little pragma and you're done. Well, MPI, at least my limited experience, is that it's not close to OpenMP in terms of non-invasiveness. You have to rewrite your code. You have to add all these message passing lines to your code, and it just looks very different. You have to think about it from the perspective of master and slaves. I personally actually prefer the way that I write CUDA code to MPI, just from the perspective of the way I think about parallelization. But that's a personal preference. But regardless, when you consider everything, I think CUDA was really probably the best choice for us. Total cost analysis. So I mentioned this. It's not just about speed up, it's about the total model cost. And this is an important slide to me because we all need to be aware of total cost of development and not just speed up. So what is for us, for our company, what's the total model cost? It's the development cost and what I call development and execution. Let's break that down. Development cost is what? Is the time and expertise needed to specify the model, defining the hierarchies, variable selection, transformation. And this is an iterative process done by a mathematician or a statistician, a PhD. Requires building, running, and inspecting early versions of the model. They're iterating over different specifications, looking at the results, seeing what works better, re-specifying the model, all of that. So this is an expensive process. When you take the And I'm going to be very sort of commercial here. If you take the money that you're paying a PhD per hour and multiply it by the time that they spend on going through this, this is an expensive process. But also there's another component, which is the time and expertise needed to convert high-level, low-performance code, for example, in R to low-level, high-performance code in C, C++, or CUDA, including debugging and testing. And that's what I get paid for. And I'm pretty expensive too. So you have these two components, and you have code maintenance. You have to think about all of this. And execution, obviously, itself has a couple of components. You can think about it in terms of wall time and in terms of number of core hours. So you can reduce wall time by going to MPI, but if you multiply cores and hours, usually you're getting worse. You're paying more because your parallelization is imperfect, right? So when you think about all of this, so how did CUDA help us? Well, it helped us because it allows modelers to iterate on the models a lot faster. Not only does it save their time, but it also reduces the sort of the expertise needed for them. So instead of having a PhD, you can basically give a tool that is more iterative to somebody with a little bit lower expertise, because then they can replace their mathematical intuition with trial and error. So it helps us save on this. But then the burden gets shifted a little bit to this side. Now you need programmers that know how to write GPU code. But then if you've come to this conference early enough, you've realized that this was a great conference for us to hear, because now we're getting more and more tools. We're getting CUDA 5, we're getting this IDE, which is fantastic, right? You have the debugger, the profiler, and everything inside of it. So this part of it hopefully will also go down. And then execution costs, well, definitely the most drastic reduction in wall time, but it's also cheaper, because when I literally did this math by looking at how much money we were spending for our little test runs on this cluster. We realized we were saving about 5 to 10 times on actually the dollars that we were spending on core hours, running GPU versus MPI. So that was pretty nice. On the other hand, again, maintaining in-house GPU servers adds to the required skill set for system admins. Our system admins, we're a small company, so it goes back to the context that I said for you. We're a small company, our system admin mainly dealing with Windows servers. And then now all of a sudden, not only does he have to deal with a Linux box, but he also has to think about, oh, what the heck is this GPU? And that's not something that he's very comfortable with. So then now the burden is on me. Not only do I have to write software, I also have to maintain the box. I have to update the libraries. I have to worry about the network and this and that. And so the GPU aspect of it adds a little bit of a sort of a issue on that respect. Oh, and I didn't talk about the vector math library. So this is a good place to talk about that. Compared to MPI and Intel's VML, CUDA requires about as much code modification. So, you know, again, there might be this little bit of myth about, you know, writing CUDA code is harder or more time-consuming or modifies your code more. In my experience, not so much. Especially now, again, we're getting better tools. We can compile separately and then link. That was kind of a pain in the butt. You had to include all these, you know, device functions, write includes, and it was just kind of ugly. Hopefully that will all get better. And then you compare to VML. I really tried VML. I was at the supercomputing conference in Seattle. I talked to the Intel engineers, and I actually got like 6-7 times performance gain out of just using VML. The problem was you can't combine VML with OpenMP. At least when I combined them, I didn't get more performance. Again, if I knew more hardware, I could probably tell you exactly what's going on. But I think these vector units in the machine, they're not. If we have 12 cores, I don't know how many vector units are there. But I couldn't multiply the performance by adding OpenMP pragmas to a sort of a VML using statement in there. So VML was great, but even vectorizing your code is non-trivial, right? You have to rewrite the code for that also. It's not like you can just take a lot of the calculations. You have to literally turn all of that into one giant for loop so that you can offload that to a vector unit. So vectorizing the code is not, again, doesn't keep the code very natural. So when I look at all of these, I'm still kind of leaning in favor of CUDA going forward, even though I do want to keep an eye on the other option, including this kind of largely hyped Intel mic, right, which we've heard about. But we'll see where that goes. But right now, I think CUDA is definitely, for us, is pretty practical. And lessons learned for people, for modelers, for developers, people are looking to start programming. This is what I think were some of the success factors. Be goal-oriented means agnostic. What do I mean by that? I'm pretty illiterate when it comes to programming, at least relatively. I just recently started it about a couple years ago, writing C code. I'm also not an expert in statistics. I'm not an expert in hardware, any of them. I just know enough about them. And I think that might have turned into a strength instead of being a weakness, because when you don't have a particular angle that you're in love with, then you just try any angle that works. So for me, I didn't care what angle was the best angle. I just said, I just want to see what works. And we just go off of that. So I think that's pretty important. Don't fall in love with performance, especially too early. Poorly written, super fast code is doomed for failure. I learned that lesson early. You go for optimization too early. If your function, then later on you realize your functionality has been compromised, you have to go all the way back, because performance optimization almost always depends on functionality. If your functionality changes, a lot of your assumptions that you made in order to parallelize your code, they're all violated. So you have to go back. So I think it's pretty important not to fall in love with performance. A lot of times I would give up performance happily for code modularity, for having nice interfaces, for portability, for maintainability, and all of that. Seek opportunities for abstraction, that's obvious, I think, but it depends on model volatility. So for us, because again, we change our functions all the time, the likelihood functions change, so we can't really implement a particular model, hard code all the function into like the slice sampler, for example. We definitely had to abstract out the function as a function pointer and feed it into the slice sampler like that. So, but for someone who is solving the heat equation day in and day out for the next 5 years, they know that's their differential equation. They don't have to worry about a lot of this stuff because, that's what you're focused on. And actually, in that case, it's better if you don't worry too much about abstraction, because abstraction usually clashes with performance in other ways. And consider software development path. We are using R to C++ to OpenMP to CUDA, because all our code originates in R. And the way we do it is we just port functions one at a time. We do a performance analysis, where are the bottlenecks, and we just port them one at a time. We create a shared library in C or C++, and from R we call that shared library. So you just swap it out and you compare the results. Debugging is easy. You go one step at a time. And literally, as my mathematician hands off the code to me, I can run in parallel with her. I can say, okay, you gave me the code, here's the bottleneck, I'm going to swap it out with the C++ code. Tomorrow I give her back the code, and it's running 5 times faster, 3 times faster. It's a little bit of improvement, right? And then while she's playing around with her next, or tuning her parameters, or picking a different component of her model, then I say, okay, what parts of your code are stable? Let me think about those and how I can port them to the GPU. So that's sort of the way we think about it. We don't jump all the way to CUDA. We go through the steps, and it's worked out pretty well. I actually parallelized for most recent project that we had this HP model that had 13 variable blocks, a total of millions of variables, and we managed by adhering to these principles of sort of code migration and using the abstractions that we talked about, I managed to port all of that within 4 weeks, which was pretty remarkable. And she could basically run a code that was hanging in R, because R is notorious for not being able to handle large data sets. Anything bigger than a few gigabytes, R crashes. So she was kicking off a code on Friday in R, coming back on Monday, and nothing had happened. The code had just hanged in there. And we got, over a course of a month, we ported most of the code to the GPU, and the same code was now running, finishing in about 1 or 2 hours. So it was pretty, we really got a lot out of using these principles. Obviously, we want to learn about the tools. I'm kind of guilty of not having used these tools as much as I should have, but the note to self and to others. And be prepared to learn about hardware as needed. We're software developers, but in this business, we need to learn about hardware sometimes. And there are some common pitfalls that I suggest to NVIDIA to really maybe have a part on their website targeted for new programmers to kind of warn them about what kind of mistakes they're most definitely going to make, and hopefully prevent some of that. So attempting block cooperation within kernels, assuming that they can talk to each other, I made that mistake. Synchronizing within divergent threads, missing thread synchronization, and invalid memory access. And now this would be helped with memcheck. And again, the tools that they're providing are going to be very helpful in terms of avoiding these mistakes. But nevertheless, I think having a heads up could definitely help. And there are some suggestions for NVIDIA as well. Again, put this list of mistakes maybe on your website. improving abstraction capabilities like using function pointers. And I've got a lot of heartburn from doing double precision on GTX card. Is there any way to kind of, I'm not expecting it to be as fast or being, I mean, I'm happy with double precision being 8 times slower than single precision, but it's another ball game if double precision is just volatile, and that's something that we've seen. I've talked to a couple of engineers here, and I think I'm getting some idea of why this is happening. But telling my CEO that they need to spend 5 times as much on the Tesla cards, I have a little bit of explaining to do. So